Okay, so today we work with infinite strings in Haskell. The first question, well, let me introduce the topic. So hopefully you remember that every continuous and infinitely derivable function can be developed as a Taylor series, right? So you can say that fx is equal to f0. Let's say we develop the function around the origin. So we can say divided by 0 factorial x to the power of 0, right? X to the power of 0 is 1, 0 factorial is 1, so they don't count. F prime, prime meaning derived once, 0, 1 factorial, and x plus and so on and so forth. The general term would be f derived n times applied to 0, n factorial x to the power of n. This is n. Okay, plus and so on, and it goes up to infinity. So we can take any function and isolate these coefficients, right? Of course, we cannot store the x, but this function would essentially be fully determined by these coefficients, which we're going to call a0, right, a1, a2, and we put these in a stream in Haskell, and we have the exact expression of any function, right? We don't have a numeric approximation of a function. We have the exact expression of any function as an infinite stream. And then, because of that, we'll be later able to compute the function to any precision we might want. So the important aspect is we don't need to make a decision about the precision right now. We can make a centralized decision about the precision that we want for our computation when we know exactly what that precision should be, right? And also the laziness of the stream will allow us to not have to compute extra elements. It's not the case that, just to be on the safe side, we're going to compute 100 terms of our function just to realize later that we only need 30. All right. When we realize that we need 30, we make a request. The request trickles down to all the expressions, and you will take from the stream exactly as many elements as you need to have a final result with 30 elements in the final result stream. So now the first thing that we want to do is have this kind of encoding of a function as a stream of infinite rational numbers. And the easiest function to express in this way is the exponential, e to the power of x, which you have there, right? E to the power of x is 1, which is essentially e to the power of 0 divided by 0 factorial, plus x, which is ex derived once, right, applied to x, divided by 1 factorial, and multiplied by x, and so on and so forth. So we want to produce essentially this stream. 1, 1, half, 1/6. So essentially all the fractions 1 divided by n factorial. That would be a representation of the exponential function. Go back to part. Yes, we have to. Actually, maybe you don't, because virtually has answered many times. Cheng, I got your solution. Will you talk after the class? Okay.
Oh, where is it? No.
So open Alt tab, go to the editor, Notepad++, dn++. Open a file, Control O, just Control N, actually, Control N, and call it G2. We're going to put all the solutions in a single file. We save it later. So let's try to define the stream. Well, let's not call it series. Let's call it e, or exponential, or x, because it's very specific, right? So go to the folder d/l. D. No, you are in D. Just okay there. D. One up. Okay. And PL. And you should find something like T08. Yes. And call it G2. .hs. We're going to stay inside this one. All right, so good, save. Move to the Haskell environment. No, yeah, Alt up, one more. And now say load, you're already in the correct directory, load g2.hs. And let's take, 10 E. All right, so to be able to appreciate it more, because all of them are real numbers and that doesn't tell us much, let's go and import data.ratio. So import capital data, capital ratio, and use a % sign at zip width.
Yep.
Instead of the slash. Instead of division, use a % sign. This is rational division. And repeat. No, load first. You can repeat the load. Yeah. All right, so now it's clearer that we have 1 divided by n factorial, essentially. Okay, very good. Thanks. What's the complexity for this? So to compute the nth number, when we compute the nth number of the string, what's the complexity of that computation? Let's say instead of taking all the numbers, printing all the numbers, I go and print E rank 10, right? Which is very clearly 1 divided by 10 factorial. What's the complexity? Is it linear?
It's just a number and then easy by to include the on one side is quadratic.
It's quadratic, right? No, so you have to include the ones, right? So it looks here that you're accessing only the 10th element, but this formula will access all the elements between 1 and 10. Okay? So the question is, can we make it linear? So if you have these kind of expressions and you don't use recursion, it's very difficult to make it to make it linear. All right. So let's look at what we want to compute. We want to compute 1 divided by 0 factorial, 1 divided by 1 factorial, 1 divided by 2 factorial, 1 divided by 3 factorial, 1 divided by 4 factorial, right? A very simple method usually is to shift this entire thing by 1. 1 factorial, 1 divided by 2 factorial, 1 divided by 3 factorial, and so on, right? And then look at, so of course this we always can provide as the first element of the stream. Look at this part. So, can I put a stream here? So put another stream here, so that every element here combined with this guy would give me this guy. And then another element here that combined with this guy will give me this guy. What element and how do I combine them? Right, so I can put the stream 1, 2, 3, 4, 5, and I can divide element wise, right? So if I perform division, I divide element wise. So I take advantage of the fact that I have computed 1 divided by 2 factorial, right? In computing 1 divided by 3 factorial. I take this guy, divide it by 3, and I get one more guy. I don't compute the factorial from scratch. Doesn't make sense. Okay? So, we can keep this here. And I'm going to call this E series because I think E is already defined. So the first element is 1, right? And then we should have zip with division, or maybe percent, E series, and 1. Okay? So we have to use recursion. Without recursion, we haven't done, we're unlikely to get an efficient computation. We might be, let me restart. There might be leftovers from the previous class. I can't use, but then if I use division, I get real numbers. But this is fractional. How do I keep it fractional? What's the type of this guy? So this guy is double. Why is it not fractional? start careful. Okay, so now it works all right. Where's the expression here? Okay, so now it works all right. So we want to keep things at infinite precision, right? We don't want to. We want to get the option of limiting the precision has to come much later. All right, so this is an expression. It computes every element in linear time, O of n. Questions? All clear? Question 2 then, exercise 2. So we'd like to compute the value and see compute values and sort of convince ourselves that the stream has the correct meaning. So what do we want to compute? We want to compute successive approximations of the value represented by the stream for a given value. So for a given argument, right? So we have this 1 divided by 0 factorial, 1 divided by 1 factorial, 1 divided by 2 factorial, 1 divided by 3 factorial, and so on, right? What we want to compute is 1 divided by 0 factorial, 1 divided by 0 factorial plus x divided by 1 factorial, 1 divided by 0 factorial plus x divided by 1 factorial plus x squared divided by 2 factorial, and so on, right? This is what we would like to do. We can do this in 2 steps. So let's first of all put x's here. So we could put x to the power of 0 here, x to the power of 1, x to the power of 2, x to the power of 3, and then figure out a way to add them up. When we want to add them up, right, so if we have a stream A0, A1, A2, A3, the stream A0, A0 plus A1, A0 plus A1 plus A2, and so on, can be computed by the scan L1 function. So we're just going to use this one. All right. So let me show you how this one works. Scan L1, 1, 2, 3, 4 will return, and of course we have to put a plus here. Scan L1. Okay. 1, 3, 6, 10. Right? So what we get is this guy 1 is 1, 3 is 1 plus 2, 6 is 1 plus 2 plus 3, 10 is 1 plus 2 plus 3 plus 4, right? So we're going to need this function once we have x to the power of 0 divided by 0 factorial, right? X to the power of 1 divided by 1 factorial, and so on and so forth. So let's see, how do we do this? Would like to try. So we're going to write a series valve, right? Takes in a series S and a value for x, and we get successive approximations of S applied to x. Would like to try.
You're supposed to get the successive. It's not one value.
Yes, it's not one value. It's a stream of successive approximations. So let's first get the stream of x to the power of k divided by ak times x to the power of k. So we have the series of AKs, A0, A1, A2, A3, and we want A0 times x to the power of 0 a1 x to the power of 1, a2 x to the power of 2, and so on and so forth, right? Then we're going to just use the scanf function to add them up. Yes? That's right.
I do the
So do the polynomial first, right? So take a series x, s, take a series s as a argument. No, use that name, series 1. Right? So first argument is s, the series, and the second argument is x, the unknown, right? So again, it has to be recursive. If you're not, I mean, you can do it non-recursively, but you're not going to get linear. No.
because I add another argument.
Oh, add it here if you want it, but you don't need it. Okay, do whatever you want to do. Let's see where. That's not going to create a stream, right?
Yeah, that's just it goes to infinite. Right? I mean,
Yeah,
it goes to infinite approximation.
that would be an infinite computation. All right, so let's go back to the beginning. Let's delete the where clause.
Yes.
All right. So we're going to have what? So we're going to have the first element is going to be the no. So the first element, let's do the following, right? So we're going to do zip width. We will need a helper function, right? So zip width of series with powers of x, where powers is where we're going to define powers. And in zip width, the operator should be star. So we put a star after zip width in brackets, a star, and then powers of x should be in bracketed as well. And you can say now where powers. So we can go to the next line and say, where we don't want to define powers as a helper, right? Where powers x equals 1 colon map, and we would have x star in brackets, x star, brackets around because it's a cut, powers x, right? Powers x also in brackets. And actually, this is not the series vowel. This is this is the polynomial. So, all right, go right after the first x. Go right after the first x, and cut and paste from there to the end. So go to select to the end of the line. The end of the line. Cut that, Ctrl X, and let's go right after where. Put an enter there. Put a return. Indent a little bit more, and then go to the where line and paste. And let's define another function called pol, P-O-L, for polynomial of x is series powers x. We might need powers to be defined first. Indent powers to be the same level with pol, or pol at the same level with powers.
Indent this?
Pol and powers should be at the same level. Otherwise, it won't work. So now we can go to series x. And now if we have the polynomial, we need to do scan L1 equals, there, yes, equals, scan L1, plus in bracket, and pol x also in bracket. So this should be save. Go to Haskell reload. All right, and now try it, right? So series val apply to each series underscore val apply to each series, and one, put a 1 initially, and enter. Sorry. Take 10. This should be infinite. No, at the beginning. So 1 was good. Leave the 1 where it was. And take 10 has to go to the beginning of the line. And you can put a $sign there.
Wait.
Either brackets around the whole thing, or put a $sign. Put the $sign right there. And a space. Okay, I'll explain in a minute. Enter. So these would be the values for the value for the successive approximations of E, right? Of the number E. Now we want to see these. We know the value of E as a real number. So let's try to convert it to a real number. So repeat the previous expression and go to the beginning. And now say map backslash x bracket backslash x, not slash, backslash arrow from rational capital from a single function, single name, from capital rational, and x, close the bracket, and another $. Good. So let's see the numeric, the double values. So you probably remember the value of E. So it's about 2.718. So these are converging towards that. You can go and take more elements. So instead of 10, take 20. So you see it kind of gets stuck to the same value, to a single value. 2.71828.182. Can you print E? Just type E and enter. Oh, we don't have it. Can you print exp1, exp1, exp applied 1? Okay, so you see we're pretty precise. So this is the exp1 stored inside, so it will be the value of E, and we're getting exactly the same thing, right? And we should, because we're using the exact expression for P. Okay, good. Thank you. Why do I use the dollar sign? The dollar sign is just a little trick. So if you're confused, you can just go and use brackets. And it associates to the right. So we get exactly the same thing. So dollar sign is just a little trick to allow us to save the typing of brackets. It's an operator that does nothing. So actually, let me show you. I'm going to create a function. Right, so f is a function. F applied to 4 is going to give me 6. So now if I want to apply f to 2 plus 3, for instance, 2 times 3. Right, the strange thing is not that strange. Function application is always applies tighter than any operator. Right? So we first apply f to 2, and then the result of that is multiplied with 3, right? So standard precedence is like this, because there's the invisible function application operator that resides here. That resides here, right? It's invisible, but it's nevertheless there. So if I want to apply f to 2 times 3, I should change the brackets like this, right? And I get f applied to 2 times 3. Now, I can use the dollar sign to achieve the same thing. The dollar sign has no meaning. It just applies f to the right-hand side, right? Just that it is defined as an operator, and it has the lowest precedence, the lowest possible precedence. But it's not a function. So then when you see it here, because of its low precedence, right, Haskell will say, well, let me evaluate the left-hand side, let me evaluate the right-hand side, and then apply the left-hand side to the right-hand side. So this 2 times 3 gets evaluated before f applied to 2. So we get 2 times 3, and we save the brackets. We don't have to type the brackets, right? So it helps us with typing fewer brackets. That's all, right? So what we wanted to evaluate was this, but because we didn't want too many brackets, we can use the dollar sign. All right. So this operator associates to the right. So this dollar is evaluated first, so we're going to get this. And then this dollar is evaluated next, so we're going to get the remainder. Right? And that's going to do exactly what we want done. Is this clear? So you can use your dollar sign to just save a few brackets, make the code more readable. Okay, questions? If not, let's move on to exercise 3. Write a Haskell function that computes the integral of a power series. So how do we do that? Integral. Right? So integral of a0 plus a1x plus a2x squared plus a3x cubed plus and so on dx is equal to what? Come on, you have to know. So there's some constant c, right, that would come in here, and we're going to give this c as an argument to the integral, plus a naught x plus a1x squared divided by 2 plus a2x cubed divided by 3 plus a3x fourth divided by 4, and so on. Okay? So now, if my stream is this, 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 and so on, my result should be this, 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 and so on, right? So that's what we want to do. Take a stream of numbers, produce another stream of numbers. Okay? Who wants to try? Yes.
Done.
Okay, very good.
Sorry? I will see. Really.
Save and
sorry.
save and run.
So what do you run with?
Integrate e, and then you know the integral of integrate the exponential, and then the integral of the exponential should be the same thing. Take 10. Don't go.
Yeah.
All right, and now do the math that I did before, so we can be sure that we're yeah, we would have like the series. No, the value. Yeah, all right, fine. It's the same. We can see that it's the same as e because it's all the denominators are the factorials, right? So you know, integral of e to the integral of exponential is the exponential itself, right? So we're verifying that. Good. Thanks. Very good. How about derivative? You, Jan? And we had Elwood, right? Elwood? Yes. Zenmin, right? Is Elwood here? Yes, Elwood. Sort of look a bit alike, so I think that. And John is here. Quanghock is you, right? So third. Somebody else. Oh no. Okay, who wants to try the derivative? Is Kim Lee here? Kuchan? Want to try? And John May, is it here? John May, not here.
So what is the derivative series?
Pardon?
The derivative of the power series. Also, it's
So,
zero. It's
when we
0,
take-
1.
right. So when we derive, say derive because we integrate, then derive. Also string L, right? Then we're going to, no, not 0. So what happens with the constant? At the front becomes 0, right?
Yeah.
But all the powers of all the x's are downgraded by 1. So essentially we want to shift the stream by 1 to the left. How do we shift the stream by 1 to the left? We use tail. Very good. Yeah, we can also drop 1, but tail is more direct. So we're going to work on the tail. We have to zip width the tail with what? So we have to say zip width. Or deriving.
Sorry? Derive?
Or deriving is the opposite of integration. So if the integration divides, the derivative should
Why do we need
So the integration divides, right? Uses division. The derivative should do what?
times the
Multiplication, right? Okay. So now we can say tail L, and we multiply with every element with
the powers.
So we divide by what in the? We divide by what
1, 2, 3.
in the integration?
Or we should by the
Okay, good. Save. And yeah, take the same thing and instead of integrate, say derive. Just reprise. Yeah, that's good. We also don't have a first element. We also don't have a first argument. You have too many arguments. 1. Okay. So again, the derivative of the exponential is the exponential itself. Right? So this is it. Okay, very good. Pang Yan Han is not here, right? Oh, yeah. Oh, yes. Oh, I did a bad thing. I put your marks to somebody else. Just one. Ling Tong is here, right? Yeah, okay. So I can take care of someone else. Then Han just answer. Okay, that's good because we haven't answered for a while. Wang Li Wei. Zupong. Want to try? The next one? Yes? Zupong. You want to try the next one? Come on. You never answer. Never ever. Come on, Zupong. So how Chang is here? Yeah, come. Li Wei. way, not here. I'll leave just joint. Lengthon is here, Yampan is here, structure is here, center is here. Turn Q. What happens to Q? I haven't seen him for some time. Airplane is here. John May. John May? John May? Is it? John May is not here. John is not here. Hong Kong just answered. Fu Chang? That's you, right? Okay. Kim Lee not here. Dale is not here. Yi Chang saw him. Chen Chang is here. All right, so the equation is what? F prime equals F, right? So whenever we say F prime equals F, the unknown is? Have you studied the differential equations in high school? Yes, right? So F prime equals F. Derivative of F equals F. The unknown is? What symbol is the unknown? F, right? It's an entire function. We want to find it. We want to find out what it is. We can't write that, right? Now, the thing is that whenever we do that, F prime equals F, we always need a constant, right? We are told that solve the equation F prime equals F, considering the initial condition F0 equals something, right? For instance. So if we would say F equals derivative of F, which could be one option, right? That equation would not work because there's no way to take into consideration the initial condition. So what can we do? We can integrate on both sides, right? We have an equation which is an equal sign. We can integrate on both sides of the equal sign, and we can say that integrate of F equals F, right? Or F equals integrate of F. And here we can also provide the initial condition. Now, so if we define it, we have to define it, what we define is on the left-hand side. So we can say, let's say, call it sol, S-O-L, for solution, equals, right, integrate, sol, and the initial condition, I think, is 1. So let's provide it as a rational number, 1% 1. Just to make sure that we do not lose any precision. So this is it. So interestingly enough, Haskell solves this for us automatically. Save. Reload. We can't do this. Oh, all right. Sorry. Go back to integrate and say 1. Just 1. Leave it as 1. Control S and reload. Oh, the constant is the first. Sorry. So put 1% 1 then. Delete that one. No. The argument is the first, right? The constant is the first. So before sol, say 1% 1. Before sol, okay. Before sol, 1% 1. Save. From the literal 1. Maybe put 1% 1 in brackets. Is that the problem? Okay, yeah. So, never do that. Take. All right, so we see again that the solution is the exponential function, right? Which we know. So the f prime equals f, we know that the exponential derived is the exponential. Could we find out, could we define sine and cosine as solutions to a differential equation? So sine, oh, you want to try?
No, can I ask?
Sure.
Why do you put 1% 1?
1% 1 is the fraction 1 divided by 1, right? We want to keep this, it's an infinite precision rational number.
I mean, what is taken as C, right?
What do you mean it's taken as C? It's the C, yes. So
why do you put the C at 1?
When you integrate, you need a constant, right? Integral of f, right, is some expression plus a constant, right? So you have to say what that constant is. The integral is not defined, or is defined up to a constant. So you can't have a precise expression unless you provide a constant, right? So sine derived is cosine. Cosine derived is, again, negative sine. Very good. Okay? Integral, 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 integral. So sine is integrate cosine, right? And the constant, we have to put a constant here, right? Should be when sine is 0, the constant should be 0, right? Cosine should be integrate minus sine, and the constant here should be, cosine 0 is 1. Okay? So we're going to do precisely that. Sorry, I'm just going to... So integrate cos series 0. I wonder what happens if I just say like this. Integrate, and we have to negate this, right? So map 0 minus sine series. And 1, right? So 1%, 1, we're going to write it. And this should be sine and cosine. I forgot brackets. Yeah, let's add brackets here. So take 10 sine series. So this is going to be sine series. Cosine series is going to be this. And let's convince ourselves, right? So we have we can use series val, right? Series val sine series at what do we know of value? For instance, pi divided by 2. Okay, we have this. No instance for floating ratio integer. Oh well. Sorry, we're just going to use 1 here. I think we don't have pi as a rational number, therefore the type chokes. Where is it? My turn to do it. So you see that it converges to 1. Let's say 20. Right, so it's almost 1. Sine of pi divided by 2 would be around 1. Cosine of pi is around -1. So you can see it converging to -1, right? Okay. Sine applied to 0 should be very close to 0. And, oh, it's exactly 0. That's very interesting. Cosine 0 is exactly 1. That's very good. And if I say pi is -1, pi divided by 2 is very close to 0, right? So this exponent is minus 15. So it's some value to the power 10 to minus 15 times 10 to the power minus 15, which is a very, very small value. It's almost 0, right? Okay. So we're sort of settled. Is this clear? So we have defined sine and cosine through solutions to differential equations. These ones, right? Comes almost for free, right? So the interesting thing is that at no point throughout the development did we have to consider a specific precision. The precision is handled at the overall level when we decide how many elements of the final result we want to compute. When we do take and say 20, that 20 will trickle down and decide at every level how many elements of every stream need to be computed. All right, which is extremely convenient. So you have the option of whatever precision you want to have at any time. If you were not in a lazy computing setting, what you would be tempted to do is compute. You go, because you see we're trickling down. We're going back to the point where we're computing this thing, right? So at every point you would say, because you can't be lazy, you would say, oh, let me compute this many elements, so as just to be on the safe side, right? So when you compute, for instance, the series value, you would say, let me compute 100 elements, so as to be on the safe side. But then at the top level, you only require 20 elements. So those 20 elements may result in not necessarily 100, right? Maybe 30, maybe 40 elements on the deeper level series, but definitely not as many as you would envisage initially. So if you're not in a lazy setting, you would waste both memory and computational effort. So this is a huge advantage. Questions? So actually one interesting thing would be to compute the actual sign of what do we compute? Cosine. So how many elements do we need to compute here to get the same precision? it's almost zero. So usually trigonometric functions will not be computed using Taylor series, right? Because the Taylor series in this case do not converge very quickly. There are a type of series called Chebyshev series after the Russian mathematician Chebyshev, whatever the first name was. Yeah. So he created a series which converges very close to the actual value in about within 7 and 9 iterations, right? Which is much faster than 20. So you see there we have 20, and we still are much further away from 0 as compared to the internal cost function. Okay, but we can take an arbitrary value. Let's say we take because 0 is not so relevant. Operating with 0 in real numbers is not so relevant. So let's say pi divided by 4, and then pi divided by 4. So let's compare the values. 707, 106, 781. So 707, 106, 781. So this one is already the correct one. Right, so we have how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, about 11 elements. Okay, so not too bad, but still. Is this clear? Okay, good. See you next time. Class dismissed.